All right, let's jump right into a physics classic. Today, we are tackling problem 1.2 from the one and only I.E. Irodov's Problems in General Physics. If you're looking for a good workout to sharpen your kinematic skills, well, you've definitely come to the right place. Let's get into it.
So, if you've ever studied physics or engineering, you've probably heard of this book. It's an icon. And Irodov is known for problems that don't just test your ability to plug and chug formulas. No, they test if you actually understand the physics. And this problem? It's a perfect example. This is all about thinking like a physicist.
Okay, so here's the problem we're up against. A point travels half the distance with some velocity v0. Then, for the rest of the trip, it goes at velocity v1 for half the time and v2 for the other half. And our job is to find the mean velocity for the entire trip. See that little twist in there? The journey is split by distance first and then by time. That's the interesting part.
Now, before we even think about writing down equations or variables, we've got to stop. We need to ask ourselves, what's the one fundamental idea that's going to unlock this whole thing? It all comes down to really truly understanding what mean velocity means.
So what is it? Simply put, mean velocity is the total distance you went divided by the total time it took you to get there. Seems easy enough, right? But here is the number one trap people fall into. It is not just the simple average of the velocities. You can't just add v0, v1, and v2 and divide by 3. It doesn't work that way. And this problem is designed to make sure you know that.
This right here is our golden rule. This is our North Star for this whole problem. Mean velocity is always total distance over total time. Every single thing we do from this point on is just a way to figure out those two things. Let's keep this in mind.
Okay, let's start chipping away at this. We're going to break the journey down into manageable pieces, and we'll start with the first half, the part that's defined by a set distance.
So first step in any problem like this, define your terms. Let's just say the total distance of the whole trip is s. That means the first half is, obviously, a distance of s over 2. And we know for this whole part, the velocity is a constant v0. Simple enough. So how long does this first leg of the journey take? Well, you know the basic relationship, time is distance divided by velocity. So we'll call this time t1. It's just our distance, s over 2, divided by our velocity, v0. And boom, we've got our first piece of the puzzle. Let's just put that on the shelf for a minute.
And now for the second half of the trip. This is where it gets a little more fun, because the problem throws a curveball. This part isn't defined by how far you go, but for how long you go. Let's unpack that.
You see the difference here? This is the whole game. The first part was simple, travel a distance of s over 2. But the second half is different. It says you travel at v1 for a certain amount of time, and then at v2 for the exact same amount of time. That little switch from a distance split to a time split is everything. Okay, so let's set up our variables for the second leg. The distance is still s over 2, that hasn't changed. But we're going to say the total time it takes to cover that distance is t2. Let's see what we can do with that. We can build an equation from this. We know the total distance for this section is s over 2, and that distance has to be made up of the distance traveled with v1 plus the distance traveled with v2. The first distance is just velocity v1 times its time, which is t2 over 2, and the second distance is v2 times its time, which is also t2 over 2.
Now for a little bit of algebra. You can see on the right side of the equation that t2 over 2 is in both parts, so we can just factor that out. That leaves us with s over 2 is equal to t2 over 2, all multiplied by v1 plus v2.
And from here, solving for t2 is pretty straightforward. The over 2 on both sides just cancels out. We do a quick rearrangement, and there we have it. t2 equals s divided by the sum of v1 plus v2. That's the second big piece of our puzzle. We are getting really close. Awesome. We've done the heavy lifting. We figured out an expression for the time it took for the first half and for the second half. Now, it's just a matter of putting it all together to get our final answer. So let's just recap what we found. For both the first and second half, the distance was the same, s over 2. But because of how each half was described, one by distance, one by time, we got two totally different expressions for how long each took. So what's the total time for the entire trip? Easy enough. We just add our two times together. We just add t1 and t2. That gives us a total time of s over 2v0 plus s over the quantity v1 plus v2. And now, we go all the way back to the beginning, back to our golden rule. Mean velocity is the total distance, which we called s,
divided by the total time, which is that big expression we just found. Let's plug it all in and see what shakes out.
And here comes the most satisfying part of the whole problem. Look at this. We have an s in the numerator, and we have an s in each term of the denominator. That means they all cancel out. How cool is that? This tells us something really important. The mean velocity doesn't even depend on how long the trip was. It's a general result.
So after we do a little bit of algebra to simplify that fraction, we arrive at our final beautiful answer. The mean velocity is 2v0 times the sum of v1 and v2, all of that divided by 2v0 plus v1 plus v2. And that's it. We did it.
So yeah, getting the right answer is great, but what's the big picture here? What did this problem really teach us beyond just the math?
Well, it really boils down to three things. One, always go back to the fundamental definition. Total distance over total time will never steer you wrong. Two, watch out for the trap of just averaging velocities. It's almost never that simple. And three, and this was the key to this problem, you have to pay super close attention to how each part of a journey is defined. Was it split by distance, or was it split by time? That detail changes everything.
Now, to make sure you've really got this, I'll leave you with a challenge. What if the problem was slightly different? What if that second half of the trip was also split by distance? You know, you travel at v1 for half the remaining distance and v2 for the other half. How would that change the final answer? Think about it. You've got all the tools you need to figure it out.